So let's take a look at limits and continuity of multivariable functions. So the standard definition of a limit, let's say we have the limit of some multivariable function f of x comma y as the coordinate pairs x and y approach some value a and some value b. So as x approaches some value a and as y approaches some value b, that is going to equal some value L. So for these problems, let's find the limit if it exists or show that the limit does not exist. So for number 1, we have the limit of x to the 5th plus 4x cubed y minus 5xy squared as x and y approach 5 and negative 2. So the very first thing when we evaluate limits is we always have to try direct substitution. So let's go ahead and plug in 5 for x and then negative 2 for y. So when we do that, we'll get 5 to the 5th, because x is 5, plus 4 times x cubed, so 5 cubed is 125, times negative 2, which is y, and then minus 5 times x, which is 5, and then times y squared, so negative 2 squared will give us positive 4. So when you use your calculator and plug this in, you should get a value of 2025. So for number 2, we have the limit of x squared over x squared plus y squared as x and y approach 0 and 0. So if we do direct substitution here, we'll get 0 squared over 0 plus 0 is 0. And so that's an undefined answer. And so we cannot use direct substitution in this case. So what we have to use is a different method. So let's say we have a 2D coordinate plane here, and we're trying to find the limit as described in this problem as x and y approach the origin, or 0, 0. So what we can do here is actually find the limit along each axis. So we can find the limit along the y-axis, and the limit along the y-axis is where x obviously equals 0, and we can also find the limit along the x-axis, and the limit along the x-axis is where y equals 0. So in this case, when we evaluate, if this function is known as f of x comma y, since it's a multivariable function, let's go ahead and evaluate f of 0 comma y, because in this case we're going to make x value 0. When I do that, we'll get 0 squared, or 0, over y squared. So obviously 0 over y squared is 0. Now let's make y equal 0. So we have f of x comma 0. So when I do that, we'll have x squared over x squared plus 0, which is x squared. So that will give us a value of 1. So notice the limit along the x-axis is not the same as the limit along the y-axis. So since 1 does not equal 0, or 0 does not equal 1, we know the limit does not exist. So it's very similar to one-sided limits, where if the limit from the left-hand side does not equal the limit from the right-hand side, then we know the actual limit doesn't exist. So for number 3, we have the limit of xy cosine y over 3x squared plus y squared as x and y approach 0 and 0. So if we do direct substitution, substituting 0 for both x and y, obviously we'll get 0 over 0. And we cannot divide by 0, so we know direct substitution doesn't work. So now let's go ahead and try making the x value 0. So f of 0 comma y, where we make the x value 0, is going to be 0 on the numerator over y squared. So obviously that gives us 0. And now let's make the y value 0. So f of x comma 0 is going to be still 0 on the numerator over 3x squared. So that will also give us 0. So if I were to draw the 2D axis, or the 2D coordinate plane once again, we found out that the limit along the y-axis is also 0, and the limit along the x-axis is 0 as well. But keep in mind, just because the limit along both the x and y-axis is the same, that does not mean the limit actually exists. So we have to find at least one more equation or line that we can substitute in. So we found, or we used x equals 0. We have used y equals 0. So now let's try the equation y equals x and see if that limit is also 0. So if this equation, or this multivariable function, can be written as f of x comma y, this time we're going to substitute x for y. So we're actually going to find f of x comma x. Once again, we're doing that because we're substituting x for y. We're going to substitute that in right there. And so when I do that, we'll get x times x, so x squared cosine of x over 3x squared plus x squared. So that will lead us to x squared cosine x over 4x squared. Notice the x squareds will cancel, and so we're left with cosine x over 4. So now what we can do is go back to the original limit notation here. So we can rewrite it as the limit of cosine x over 4 as x and y approach 0 and 0. So notice there is no y value in the function, so we don't have to worry about that. But the x value there is, and we're trying to find the limit as x approaches 0. So we'll go ahead and plug in 0 for x. So we'll get cosine of 0 over 4. Cosine of 0 is 1, so we'll end up getting 1 over 4. So notice the limit across, or the limit along y equals x, the equation that we use to substitute, 1 over 4, does not equal the limit along the x-axis or the y-axis, which we have found to be both 0. So this tells us that the limit does not exist because it's not equal along all equations. So for number 4, let's say we have the limit of xy over the square root of x squared plus y squared as x and y approach 0 and 0. So obviously by using direct substitution, if we go ahead and plug in 0 for x and y, we'll get a denominator of 0 and we can't divide by that. So let's start by making the x value 0. So if we do that, let's say we evaluate f of 0 comma y. We'll get 0 on the numerator, and we'll get the square root of y squared. So obviously square root of y squared is y, but still we'll get 0 as well. Now if we plug in, let's say y equals 0 this time, so we have f of x comma 0. We'll still get 0 on the numerator, and on the denominator we'll get the square root of x squared, or x. So that would also give us a value of 0. But since the two axes have the same limit, we still need to find another equation to verify that this limit exists. So let's go ahead, like similar to the last problem, let's use y equals x, that equation. So we're going to evaluate f of x comma, now instead of y we have x because we made the x substitution for y. And so when we do that, we'll get x squared on the top. And I might actually move this a little bit. So we'll get x squared on the numerator over the square root of x squared plus x squared. So we'll get x squared over the square root of 2x squared. So we'll get x squared, and I can simplify the denominator or get rid of the radical by saying the square root of 2x squared can be rewritten as the square root of 2 times the square root of x squared. Square root of x squared is obviously x. So we'll get x squared over x times the square root of 2. Now obviously one of the x's will cancel, so we'll get x over the square root of 2. And now we can go ahead and rewrite that limit, the original limit. So we have the limit as x and y approach 0, 0 of x over the square root of 2. Since we don't have a y variable, we don't have to worry about the y limit. But we do have an x as x approaches 0. So let's go ahead and plug in 0 for x, and we'll get 0 over the square root of 2, which is 0. Now since the limit for the equation y equals x, the line y equals 0 and the line x equals 0, since they are all 0, that tells us that the equation or the limit does exist, and the limit is 0. So for number 5, we have the limit of x squared plus y squared over the square root of x squared plus y squared plus 1 minus 1 as x and y approach 0 and 0. So obviously direct substitution will lead us to 0 over 0. So we have 0 on the numerator, and then the square root of 1, which is 1, minus 1 is also 0. So we cannot use direct substitution. Now let's go ahead and try to make x equals 0 and evaluate there. So if we could evaluate f of 0 comma y, where x equals 0, we'll get y squared on the numerator over the square root of y squared plus 1 minus 1. And so if we use the original limit then, the limit as x and y approach 0 and 0 of the equation y squared over the square root of y squared plus 1 minus 1. There is no x, so we don't have to worry about that. But we do have the y approaching 0. So if we plug in 0 for y, we'll get 0 over the square root of 1 minus 1, which is also 0. So that is also undefined. And realize that if we also evaluate f of x comma 0, so we make y value 0, it will also lead to the same answer. So we cannot use this technique. So when I first did this problem, the only thing I could think of was substituting in the equation y equals the square root of 2x. So I was going to substitute the square root of 2x in everywhere for y. And the reason why I did that was because in here I could create a perfect square trinomial, and when I take the square root of that, it'll get rid of the radical. So let's go ahead and try this. So we do f of x comma, now y is going to be replaced with the square root of 2x. So I have x comma the square root of 2x. So when I do that, we'll get x squared plus the square root of 2x squared is just 2x over the square root of x squared plus 2x plus 1, and then minus 1 on the outside. So since x squared plus 2x plus 1 is a perfect square trinomial, I can rewrite it. So we have x squared plus 2x over, I can rewrite that as x plus 1 squared. So the square root of x plus 1 squared, that'll just get us x plus 1. So we have x squared plus 2x over x plus 1 minus 1. Obviously plus 1 and minus 1 will cancel. So we're left with x squared plus 2x over x. Notice I can take out an x from everywhere. And so we're left with x plus 2. So now we can go to the original limit here. So the limit as, now remember there's no y, so we can go ahead and eliminate the y. I'll just write as x approaches 0 of x plus 2. Go ahead and direct substitute, and we'll get 0 plus 2, which is 2. And so even though we weren't able to use x equals 0 or y equals 0, y equals the square root of 2x was our best substitution that we used, and we ended up getting 2, which actually is the correct answer. So for number 6, we have the limit of 2x squared y over x to the 4th plus y squared as x and y approach 0 and 0. So obviously with direct substitution, it will lead us to 0 over 0, so we can't use that. So let's go ahead and make x 0 first. So f of 0 comma y is going to be 0 on the numerator and then y squared on the denominator. So we'll end up getting 0. And if we make y 0, so we have f of x comma 0, we'll get 0 on the numerator and then x to the 4th on the denominator. So that will also give us 0. So the limits along the two coordinate axes, x and y, those are 0. So now we need to pick one more substitution to verify that the limit does or does not exist. And so the equation I'll pick is actually, instead of y equals x, I'll pick y equals x squared. And the reason that is let's say I pick y equals x. So then we're going to substitute f of x comma x. We'll actually end up getting the limit as 0, but when we substitute in y equals x squared, we'll get something else other than 0. So if I do that, x comma x, just substituting the equation y equals x, we'll get 2x cubed over x to the 4th plus x squared. So I can go ahead and also factor out x squared from the denominator. So we'll get x squared times x squared plus 1. And on the top we have 2x cubed. 2 of the x's will cancel, so we're left with 2x over x squared plus 1. So when I set the limit notation here, obviously there is no y variable, so I don't need to worry about that. So let's just say the limit as x approaches 0 of our function here, 2x over x squared plus 1. And so that will give us 0 over 0 plus 1, 1. So that will give us 0. So now let's try plugging in y equals x squared now. So when I do that, we'll evaluate f of x comma, and so we're replacing y with x squared. So when I evaluate that, we'll get 2x squared times x squared over x to the 4th plus x squared squared, which is obviously x to the 4th. So we'll end up getting 2x to the 4th on the numerator over 2x to the 4th on the denominator. Obviously that's going to be equal to 1. So the limit along y equals x squared is 1, which is obviously different than the limit along the x-axis, the limit along the y-axis, and the limit along y equals x. So since we get a different limit here, obviously 1 does not equal 0, so the limit does not exist. So the main strategy here is to pick a substitution like y equals x squared that cancels out most or basically all of the variables. So in this case we could cancel out all of them, so we just got a singular value. And so that is usually the best route to go. So now let's say for number 7 we have the limit of e to the raised to the power of negative x times y times sine of pi times z over 2 as x, y, and z approach 3, 0, 1. So even though we have 3 variables, it works the exact same way. The process is the exact same. So first we're going to start off with direct substitution. So when I do that, we'll have e to the negative x, so negative 3, times y, which is 0, times sine of pi times z, so z is going to be 1 over 2. So obviously negative 3 times 0 is 0, and e to the 0 is 1. So then 1 times sine will give us sine of pi over 2. And so sine of pi over 2 is obviously equal to 1, so that is the limit. So let's go ahead and determine the set of points at which the function is continuous. So for number 1 we have f of xy is equal to sine of x times y over e to the x minus y squared. So in order to find where the function is continuous, we could easily look at where the function is discontinuous. So obviously we cannot divide by 0. So let's go ahead and set e to the x minus y squared equal to 0. So for this I'm going to go ahead and isolate y, because no matter what I plug in for x, e to the x is never going to equal 0. So if I add over the y squared and flip the equation around, we get y squared equals e to the x. And so then we can say that y equals plus or minus the square root of e to the x, which can also be written as y equals plus or minus e to the x over 2. So since the denominator equals 0 when y equals plus or minus e to the x over 2, that means for our restrictions we have to say that y cannot equal plus or minus e to the x over 2. So the way we write the set of points at which the function is continuous is similar to the domain, where we write it in set notation. So we have to have the curly brackets. We say for all ordered pairs x comma y such that, and then we can go ahead and state our restriction here. So y cannot equal plus or minus e to the x over 2. And those are going to be a set of points for which the function is continuous. So now for number 2 we have f of xy equals, now it's sort of like a piecewise function here. So the top one is x squared y cubed over 2x squared plus y squared if x and y does not equal 0, 0. So this function exists everywhere except for 0, 0. And then we have f of xy equals 1 if x and y are exactly equal to the coordinate points 0, 0. Now let's just start off with f of xy equals 1. So let's see where that is continuous and if it has any restrictions. So remember that when we have two input functions, f of xy, we can also replace it with z. So we can say z equals 1. Now remember that z equals 1 is going to be a flat horizontal plane that intersects all points in the three-dimensional coordinate system that have a z coordinate of 1. So basically it is continuous everywhere, because no matter what you plug in for x and y, you will always get the z value of 1. So let's look at the top function now. So if we plug in 0, 0, obviously we can't have a denominator of 0 because we can't divide by 0. So that is one place where that function is discontinuous, or that is one restriction. Now obviously, as mentioned before, if we plug in 0, 0 to the bottom equation, we'll get 1, because no matter what we plug in for x and y, we'll always get 1. So we know that when we plug in 0, 0 into the top equation, it does not exist, or is undefined. And then when we plug in 0, 0 to the bottom equation, we'll get 1. So obviously these two are not equal to each other, so we know there is a discontinuity, and this is one of the restrictions, exactly at x comma y equals 0, 0. So now let's check if there are any other restrictions with the top equation. So obviously we can't divide by 0, so let's check if there are any other values that we can plug in for x and y that give us 0 on the denominator. So we can go ahead and say that 2x squared plus y squared equals 0. So let's just go ahead and isolate y. So then y squared equals negative 2x squared. And so y equals plus or minus the square root of negative 2x squared. So since we have a negative under the radical, this is obviously imaginary, so we know that there are no real y values we can plug in to get a 0 on the denominator. Now same thing goes with x. If we isolate x instead, we can say 2x squared equals negative y squared. So x squared equals negative y squared over 2 and then x equals plus or minus the square root of negative y squared over 2. So this is also going to be imaginary. So this tells us that there is nothing else other than 0, 0 that we can plug in to make the function discontinuous. So when we go ahead and write our set of points similar to set notation here, with curly braces on the outside, we can go ahead and say for all ordered pairs x comma y such that, now we can go ahead and state our domain, that x and y, now instead of equals we have to say it cannot equal. So x comma y cannot equal 0, 0. So this describes a set of points at which the function is continuous.